Hello, this is just going to be a quick video explaining 2's complement and how to do some math with it. Okay, so a refresher on how normal binary works. So you have a 4-bit number, right? Each bit is going to represent, some value in a place. So, you have your 1's place, your 2's place, your 4's place, your 8's place, etc., but this is for example, right? And you can see, least significant bit is 2 to the 0, most significant bit is 2 to the n minus 1, right? That's if you have a, right? And so, consider this 4-bit example, 1, 0, 1, 0. That's going to give us 8 plus 2 is equal to 10, right? Makes sense? Okay. So 2's complement is just an encoding, and all you do is you just say, we're going to treat the most significant bit as a negative value instead of a positive value, right? And that's not saying like that leftmost bit is saying, oh, it means a 1 and a minus. No, it basically means instead of saying 2 to the n minus 1, it's going to say negative 2 to the n minus 1. So we get the 1's place, the 2's place, the 4's place, and the negative 8's place. And this is a 4-bit example, but if it was an 8-bit example, it would be the negative 1/28th's place, right? Okay. So as an example, consider the signed 4-bit number 1010. We're going to get negative 8 plus 2 is negative 6. And it is really just a human construct. To the computer, it's all just bits. But what's great about the way that 2's complement is done is that our existing hardware to, like add numbers and such still works, which is very great. And so as an example, we have negative 4 plus 5, right? Here's the encoding in 2's complement of negative 4, and here's the encoding in 2's complement of 5. That is a 4-bit 2's complement, right? We can agree just by looking at this that this should be 1, and so let's verify that, right? We have 1, 0, 0, 1, 0, carry the 1, and you throw out, in this case, because you want to keep it as 4 bits, you're going to throw out the carry bit, right? And we can all agree that that is 1, because, that's the only positive bit, and that's the 1's place. So it just works. Now, most people will just give you a magic formula to say, oh, this is how you go from A to negative A. And I'm going to explain to you how you actually get to that formula. So consider for the following for a second, right? Let's say we have A, and let's say we have an inverted A. So all the bits are inverted, right? And this could be just some arbitrary thing, right? Well, I think, no matter how many bits our number is, I'm just gonna, like if I just say, like 1, 1, 0, 0, 1, 1, right? Inverted A, right, is gonna be 0, 0, 1, 1, 0, 0. I think we can all agree that if we added these two numbers together, we'd get 1, 1, 1, 1, 1, 1, right? And this would be the case regardless of how many bits we have, right? But what does 1, 1, 1, 1, 1, 1 represent? Well, it represents negative 1. Because if you think about it, that most significant bit is going to be, negative 2 to the n, and the sum of all the bits below that is going to be equal to, 2 to the n minus 1 minus 1, right? So, this bit, right, is negative 2 to the n minus 1, right? And then all these bits here, that's equal to, 2 to the n minus 1 minus 1, right? And so all 1's is how you represent negative 1 and 2's complement. And, you can do the math and add it up, right? So we start by saying A plus inverted A, right? A plus inverted A is equal to negative 1. And it's like, okay, so who cares, right? Well, you can say inverted A, right, is equal to negative A minus 1, and then you solve for negative A, and so you end up with, that plus 1 is equal to negative A. And so in order to get, sorry, I was talking really quiet there, wasn't I, right? But I hope you followed that algebra, right? So, add A in an inverted A, you get negative 1, and you just move it over, right? And then you just solve for negative A. So you can say to negate a number, right? So to get negative a, you just invert all the bits and add 1, right? Invert the bits and add 1. That gives you a negative number, right? And so as an example of this, you can use that to subtract 2 unsigned numbers. And believe it or not, this works. So if we just treat this as, oh, what's 12 plus negative 5? Well, to get negative 5, we take 5, right? And then you're going to, invert the bits. So 1, 0, 1, 0. And then, add 1, right? And so if we said 12, and this is unsigned, so this is an 8 and not a negative 8, but it still works, right? And if we add it to our negative 5, right, we can all agree here that we're expecting to get 7, right? 12 minus 5 is 7. And we actually do this math here, right? And then, as I said, throw out your carry out bit, right? What is this? What is this? But 4 plus 2 plus 1 is equal to 7. So you can see that it did in fact work. Now this is something important, is overflow, right? So let's say you're adding 2 positive numbers and you got a negative number. Well, that's no good. That is an overflow. Or you're adding, right? So what do you do? Like, because if you're expecting, if you're expecting something to be some value, some sign, but you got a different sign, that's not good, right? And this happens because, with an n-bit encoding, you can only encode in binary, 2 to the n minus 1 possible values. So that's why this can happen. So you could be doing something that, you can't possibly fit into how many bits you have, right? So luckily, to resolve this, you can break this up into cases. So, you can have both positive, differing signs, both negative, right? Let's look at the both positive case. So as I already mentioned, you can have a case. So for example, let's just say 5 plus 3, right? Well, 5 plus 3, our encoding of 5 is 0, 1, 0, 1. And encoding of 3 is 0, 0, 1, 1, right? We add them together, so you can get 0, 1, 0, 1, 0, 1, 1. We were expecting 8, but a 4-bit binary value that is signed, a signed 4-bit value, cannot possibly encode 8. So we actually got negative 8. And that's no good, right? That's no good. But you would agree that both these inputs are positive, right? So, if A is positive and B is positive, but C is negative, that's bad, right? So we can just look at the sign and, we're looking at the case where they're both positive. So I'm just going to say, the sign, the most significant bit of A, which tells you if it's negative or not, positive or negative, right? But you can just say, oh, the sign of A, right? And if it differs, right, which you can use an XOR from the sign of C, right, from the sign of C, right? So if the sign of inputs, which, in this case, they're both the same, but they're both positive. So I guess this is all just a 0 here. Just forgive me for that for a second. This XOR is going to come back for later for a reason, right? And XOR tells you if things are different, right? So this is going to say the sign of our input values is different from the sign of our output, because when you add 2 positive values, you're always expecting to get a positive value. But if you got a negative value, that's no good, right? And now, what about when A is positive and B is negative? Well, I'm actually going to propose to you that this will never overflow if A is positive and B is negative, right? And for example, because B is it's gonna give you some value smaller than A, right? B can be anywhere from I'm just gonna again using 4 bits, but it works regardless without loss of generality. I'm just using 4 bits because my brain is makes it easy for me to do the math, right? You're gonna say that this value is gonna somewhere less than A, right? If it's gonna lower the value, you're gonna underflow, right, and go back up to big thing. So if you just look at the smallest value that a can be, if a is positive, the smallest positive value is 0. If you look at the largest negative value of b, well, that's just that's -8, right? But in non-coding, right? So if we have 0 and we add it to -8, we're still going to get -8, right? It's going to work no matter what. You can even brute force it with all of these and show that, yes, if you look at all the cases where a is positive and b is negative, it's now going to overflow. But it won't overflow. So we can just move on. And same thing here. If a is negative and b is positive, we're never going to reach an overflow. And I invite you to try to figure out why. But yeah, it's never going to overflow in this case. You're always going to get a value that lies within the bounds that you can store. And I guess actually the way I can say this is, like, if you have, like, let's say you have a 4-bit number, 4-bit signed numbers go all the way from -8 inclusive to 7 inclusive, right? And I think you can agree that if you look at all the positive numbers, so 0 to 7, right, and all the negative numbers, right, from -8 to -1, if you pick one number from that and one number from that, right, it's always going to lie within these bounds if you add them together, right? Because you look at the extreme, the smallest number you can get, 0 plus -8, well, that still lies within the bound of -8. The biggest number you can possibly get from that is 7 plus -1 is 6, which still lies within the bound of that, right? So if the signs are different, right, it's still going to work. There's no overflow. It's always going to lie within the bounds. So it will not overflow if your signs are different. And once again, if a is negative and b is negative, we can overflow again, right? So if we said, -6 plus -3, right? A -6 and a -3. Is that -6? That is -6. Yes, -6, -3, right? -9 is not within the bounds of a 4-bit number. But we can look at that and we can just say, just humor me, say that this will overflow. So 1, 1, 1, 0, and throw away the care of it, right? We have 7. 7 is not equal to -9, because you can't store -9 in a 4-bit value, right? But it's the same thing as earlier, where look, if our sign, so a and b share signs, right? We can agree that the sign of a, which if you just look at the most significant bit, will tell you the sign, and the sign of b, right? The sign of b, not the sign of a, right? You can get the same signs. So if I'm just going to use a as an example, but it's the same as the sign of b. So if you just say, oh, the sign of a, it differs from, and this is c is equal to a plus b, right? If it's different from the sign of c, right? And remember, the sign is going to be given by the most significant bit, right? That shows if an overflow has happened. And so as a result, right, all you have to do is say, check if the signs are the same, right? And so a n minus 1, b n minus 1, that's the sign of a, that's the sign of b, and you XNOR them, because remember, XOR tells you if two inputs are different, XNOR tells you if two inputs are the same, right? So this is going to tell you if your inputs, right, if your inputs have the same sign, and if your if the output has a different sign than the inputs, right? So a n minus 1 and c n minus 1, right? So if you XORed together, that's going to tell you if they're different. So if your input signs are the same, and then the sign of your inputs compared to your output is different, you have an overflow. There you have it, right? And as an exercise, you should consider, how do you detect if overflow occurred with a minus b, right? And this is important, right? This is important because of your less than comparator, right? That's why this is important. And you do this by saying, oh, well, it's equal to a plus negative b. And these are gonna probably just get inverted or whatever, but you do want to consider it because you want to check, because if overflow occurs in your less than comparator, that's bad news. And you're going to get invalid results. So, there you go. I hope that this is helpful. Have a great day.